Hi, this is Jeff from the Ozark Mountains, that's in Missouri in the USA. Today we're going to take a look at the process of designing and engineering a MOS 8701 clock chip replacement. As you may know, these were used in the later Commodore 64s and 128s to generate the clock for the VIC-2 chip. Commodore had simplified the circuitry from the earlier C64, which used several chips, into one custom chip, which both saved on board space, cost, and it reduced the need for a separate RF shield around that part of the circuit board. With age, all chips fail, and this being a unique part to Commodore, it's not readily available anymore. So in this episode, we're going to take a look at what's involved in the design and engineering of a modern replacement, so we have 30 plus more years of Commodore clocking enjoyment. Let's get started. You might remember a few months ago we refurbished a Commodore 64 that was being donated. It had a bad 8701 clock chip, so I borrowed one out of a Commodore 128. Well, now I needed a new clock chip, so I did some looking around and I found that some modern replacements were available, but in relation to the amount of space that was in the Commodore 128, these modern replacements were huge. Then I remembered that another YouTuber, Frank, IZ8DWF, did a video about a year ago where he created his own 8701 replacement using a more modern clock chip. So I rewatched his video and found it very informative, and Frank was even nice enough to share his schematic. So he'd done a large share of the work for us already. Thanks, Frank. My list of requirements for this project is that it would be relatively easy to build, inexpensive, and it would just drop in and work in place of the original 8701. I knew the chip Frank had used would do the job, and it seemed like the real trick would be fitting it in the small space available in the Commodore 128. Basically, stuffing 5 pounds of flour in a 3-pound sack. Well, let's see how that worked out. I started with measuring the Commodore 128 to see what the maximum size circuit board I could use for my replacement 8701. This turned out to be about 1/2 inch by 1 inch or 12 millimeters by 25 millimeters. And then referencing Frank's schematic here, I started to plan and draw up my own board, and it quickly became apparent that I was not going to be able to fit the clock chip in between the 0.3 inch centers of the standard DIP 16 package. So if we look at dimension E here, which is the maximum width of the legs, which is this line right here, we see they go from 228 mil to 244 mil. And remember, we only had 3/10 of an inch, which is 300 mil, to fit that chip in there. So there's not a lot left. And if you consider the holes for our pins are going to be about 1 millimeter in diameter, and we need some space in there so things don't short out, there's just not any room left. So how do we make this chip fit then? Well, one idea was a 2-stack design where the chip was mounted on a top board and the rest of it was mounted on a bottom board, and somehow these two boards were connected together. As a matter of fact, Appy Paul did a design like that, which I'm showing here. Another idea was to modify the pins on the device itself so they folded under, sort of like a PLCC package. That didn't seem very practical though. Passy did something similar to that, where he trimmed the legs back a little bit and then modified the footprint for the SOP 28 library to make it fit. But as you can see, things are really tight. I also thought of using surface mount pin headers that would mount on the bottom of the board. And I even laid that out, but when I got to looking at the pricing for buying these sort of pin headers in small quantities, they were actually pretty expensive. The other issue is you would need some method to keep them in alignment while you soldered them onto the bottom of the board, and I wasn't sure how to go about doing that. And then I found this commercial product, which is a lead frame that's made to clip onto the edge of the board, be soldered in place, and then the carrier part on the top and bottom are snapped off. This would have been perfect, but they're impossible to get in small quantities. So then I remembered somebody telling me a year or so ago that they had used these Arduino stackable headers for pins for IC replacements. These are the ones that have the rectangular profile pins, not the square profile. But I didn't have any of these, so I tried it with some capacitors. The diameter on these legs is about right. It seemed like they would bend okay when I tried to do it by hand, and then I 3D printed this little fixture so I could set them in here like this and tighten these screws down and use a screwdriver to push the legs down. And this got me some legs that were about the right shape, and I could stick them through a piece of perf board like this, and that looked about right. So I thought, well, this looks promising. So then I ordered some of these style, and I had to email several places so I could find the ones with a rectangular profile, and to make sure that this thinnest dimension here is less than 0.5 millimeter, which is important. But my little 3D printed test fixture here just wasn't up to the task. You can almost see there how it dented the plastic already. So I machined this fixture, and this is kind of similar to the first. You put your pins in like this, tighten it up like so, and you can see where the pins are sticking through there. Then you have this punch here, which has a slightly radiused edge. And I like pushing the pins down one at a time. It's a little easier that way. So, and then when you take this apart, I can find the right Allen wrench. You take this apart, you have some legs with a Z-bend. That looked promising, and again, trying that in some perf board. That looked like it would do the trick. So this looked like a good way to go. So the next thing I did was machine out a sample circuit board, and yeah, with these size features, it doesn't come out really nice. And I wasn't going to try to build this. I just wanted the size and the pin spacing. And I soldered some of my newly formed pins on here, and most of them have fallen out by now because this didn't come out very good. But this was enough to show me that, yes, indeed, I could solder these pins in and wind up with a 3/10 of an inch spacing, and this might just work. Now that I had a good idea that the Z-bent leg idea would work, I had a few prototype boards made by Osh Park, and they look like this. You notice it has the octagonal outlines here on the pin headers, and this used Sven's cut pad library, although in the preview from Fusion 360 it doesn't look quite right on the actual board. It looks fine. This checked off most of the boxes on my wish list, everything except for the user had to configure it for PAL or NTSC. So this is one of the 3 original prototypes of version 1. This works perfectly, but you have the 2 cut pad jumpers here. You solder over the one for the mode that you want. The bottom is for NTSC and the top is for PAL. And I've had this inserted and pulled out dozens of times in testing. Then I had the idea of using a single gate inverter to automatically configure NTSC or PAL based on the not PAL input to the 8701, and I created this board design. So we have our little inverter gate right here. This is a 5-pin SOT23 package. I didn't quite have the right model, so it just looks like a black block. And we have our 10K pull-up resistor, and to make all that fit in there, I had to slide up the ICS 525 chip and slide up the capacitors a little bit. While electrically this worked fine, you might notice how small the drill holes are here. I missed that. These are only 32 mil and they should have been 40 mil or 1 millimeter. So while this worked electrically, it was very, 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 very difficult to assemble. So I changed the drill hole size and moved the inverter gate down just a little bit to make a little more room for soldering that resistor. And it looked like this version. So yeah, I also added circles around the pads instead of just having that blank. I thought that looked nicer, and I cleaned up the silk screen so there wasn't a bunch of extra lines. And this is what the final version looks like. And you notice one thing that Fusion does wrong, it doesn't show the copper color for these part of the pads right there. That's just a bug in the program. This is version 2 of the board. You notice there's no outlines around the pins. Here's one of the 3 prototypes I did not build because the holes were too small. It was way too difficult. But this works perfectly electrically. The inverter does its job. The chip can set itself to NTSC or PAL based on the not PAL input, just like the real 8701. So this showed that the inverter gate was a good idea. I just needed to improve the layout a bit. And here is version 3. This is what the final version will look like, except the final version will be blue, not purple. As you can see, the silk screen's been cleaned up, and I added circles around the pins. I think that looks nicer. And there'll be a V3 on the back here. Other than that, it looks exactly like this board. To give you a size comparison with the original 8701, here is the original chip. So it is a little longer. It is, of course, wider, but it's still pretty tiny, and it actually fits in the Commodore 128 or the Commodore 64 with no modifications. You can see the pins stick down about the same distance. So all in all, it makes for a pretty good replacement. Here's the schematic of our little 8701 replacement. It's got 2 main parts. One is the ICS 525 clock chip, which is this big chip right here. And then we have this little single gate inverter, which just toggles one line based on the not PAL signal to set it to either NTSC or PAL. This ICS 525 is what they call a user configurable clock chip. You notice there are lots of inputs here. We have the S inputs, R inputs, and V inputs. And you can leave these open. They have internal pull-up resistors, or you pull them to ground, and that programs the internal division of the clock frequency. So whatever your clock frequency input is, it can either be a crystal oscillator by itself or just a crystal here on the clock inputs. Whatever frequency that is will be divided down by whatever you have programmed here. They even have a calculator program you can download where you can input things like your duty cycle requirements and how accurate you need the clock to be, and it will tell you how to set all of these settings. There's a couple different ways you could configure this. If you try to make a really tight duty cycle, keep it between 45% and 55%, you wind up with about 200 parts per million error in the output frequency. If you do it like Frank did, which is the way I have it here, you wind up with almost no output error. There's about 0 parts per million frequency drift, but your duty cycle range is in the 40 to 60% range, which is just fine for the Commodore 64. Some of you may have noticed when we looked at the PCB layout already that pin 1 on the clock chip is in the opposite corner of pin 1 on the 8701. Well, there's no right or wrong way to do this. It just so happens that with the ICS 525 clock chip upside down with respect to the 8701 footprint, that all the traces just work out better and everything's a much more direct route. So I did it that way. Well, now that we've seen a little bit about the design of the board, what do you say we build one up and then we'll take a closer look at the testing jig. Here is our general layout for soldering. You can see in the upper center there, I've got the camcorder set up to film the soldering. Normally I would have the board I'm working on closer to me, but this is what I had to do to get the shot. On the left we have our roll of solder and our paste flux. Center left here is the circuit board that we're going to be soldering up, and it is taped down to a larger board to make it easier to handle. And in the upper right is all the parts that we'll be soldering on laid out in order. And in the upper right you can see the soldering iron, and lower left is the tweezers that we'll be using to place all those tiny parts. Well, let's go ahead and start soldering up our MOS 8701 replacement board. Here we have our circuit board. I've taped it down to a larger board using some Cap 10 tape. This not only helps keep it in place, but it also keeps me from accidentally soldering up the through holes. The general idea is to start with the smallest parts and work your way up. Here we have the 0.1 microfarad bypass capacitors. So we'll put a little flux down there, and we'll use the tweezers to put the capacitors roughly into place. I'm using rosin paste flux here, but there are many different types that would do the same job. And then using just a drop of solder on the tip of the iron, we'll just tack one side of each capacitor into place. So while tacking the parts down, we'll just try to keep them centered and flat against the board. Then I like to rotate the board around so I can always work from the same side with the soldering iron in my right hand, and we'll tack the other side of these capacitors. And I notice that that one's not quite centered, so I'll take this opportunity to rotate the board around and slip it up into place a little better. Then we can rotate the board back around and get that second side of C1. Just a dab of solder. Now we'll move down to the other end of the board and get the two 33 ohm resistors, R1 and R2. Same idea. Tack one end of each, rotate the board around, and tack the other end. Of course, we're applying flux before soldering each component. Now we're going to move on to U2, which is the little single inverter gate. It's easier to solder this before R3, which is the 10K resistor right above it. We'll tack one pin, check for alignment, and then tack the opposite pin. I'll come back toward the end and clean up the soldering on this part with a different tip. Right now, I'm just trying to tack it down into place. Now we'll get R3, which we'll solder just like the other small chip parts. Tack one side at a time. This is a 10K pull-up for the input of the inverter. Now we'll apply some flux for our clock chip, and notice the white dot down here which indicates pin 1. We'll take our clock chip and drop it into place and nudge it around carefully to get it lined up. Now I've switched to a different tip here. This is an angled mini wave tip. It has a little concave section on the tip which helps hold a ball of solder there. And I'm just going to tack one corner, and I'll check alignment. Here I'm kind of nudging it over slightly, and then I'll tack the opposite corner. This just holds the chip into place. Now I'm looking at it under the magnifier. This gives you an idea of what I see through the magnifier. It's not a great view, but it's good enough for this type of board. I'm going to apply some more flux. You can see I still got the magnifier partially in the way. I've put a little more solder on the tip of my iron, and I'm going to tack the other two corners just for good measure. And then I will just drag it right down the row of pins and solder all of them that quickly. And this does tend to leave a little blob of solder at the last pin, which you can clean up sometimes with the iron itself with the help of a little additional flux. And some solder braid can come in handy here too, just to clean up that little blob. Now we'll give the board a bit of a look over, making sure all the pins on the main chip there look okay. And then I'm going to take my angled tip here and touch up some of the solder on the other parts to get rid of excess solder and make it look like a more professional job. With everything soldered up, we'll go ahead and release the board from the Cap-10 tape and put it in a little container with some alcohol and give it a good scrub. This will let us get a really good look at the board without all that flux on there to make sure we're happy with all the soldering. And I'm looking at the board again under the magnifier, making sure I'm happy with all the solder joints, especially on that big 28-pin IC package. For soldering the pins onto the circuit board, I'm going to be using a fixture I made out of some blank circuit board material, and I drilled out on my CNC machine. You could also glue together a stack of single-sided perf board like I'm showing here on the right, and some people have told me they use an old piece of prototyping board for this purpose. Now it's time to solder our Z-bent legs on there. So we're going to put plenty of flux on both the top and the bottom of the board. And we'll slip our pins through so the Z-bend goes toward the middle of the board like this. Now we have both sets of pins in there. And then we'll slip it through the holes in our soldering fixture. This is kind of tricky to do on camera, so I'm kind of lifting the board up here to give me a better view of it. But that's what it looks like. And you want to push down the pins so they are seated against your soldering fixture. And then I'm going to solder one corner, push down on the board while I'm holding it. I just make sure that that's flat as possible. And I'll do another pin, and I'll work my way all around the board doing the four corners like this to make sure the board is nice and level. Now we'll do the rest of the pins, and notice I'm keeping the iron on there 3 to 5 seconds, and I'm applying plenty of solder. I want to make sure the solder wicks down through the through hole and onto the bottom part of the board and across that Z-bend of the leg. Now we can take it off the soldering fixture and give it a close-up look. I'll look at it under the magnifier, and I'm going to touch each pin with the soldering iron real quick. This just lets the solder flow across that extended pad on the bottom and make sure that our Z-bend legs are on there nice and good. Here's a look at the pins through the magnifier, which kind of distorts the view, but you can see they're nice and straight. Now we need to trim our pins down on the top side. I first like starting right up near the plastic and just getting those plastic pieces off of there. Trim one pin at a time. Then we can come back and trim each pin closer to the board, and I like putting my finger over top of the pin before I snip it. That way it doesn't fly everywhere. I like letting the board soak in some alcohol for several minutes, and then I'll take it out and I'll give it a good scrub with the toothbrush and let it dry off, and now we have a nice clean board. So here is the little testing jig. This is just a simple board I machined out, based it on the clock section out of Commodore 128, which has several capacitors in there. Here I've got a 10 microfarad and a 0.1 microfarad. 10 microfarads probably not needed, but it's there. And the switch just lowers the NOT PAL line, so I can make sure that that inverter gate is working. And I used a socket for the crystal as well. That way I can test crystals with it. And I just used some pin headers for power. This one's a right angle. And to hook the scope probes up to. And I wish I would have made this one a little longer. It would have been easier to get both probes and both ground leads on there. And I also wish I would have put a power switch directly on this. So I designed a new one of these. I haven't built it yet though. It's got a little power switch up on top here, which would make that easier. But the basic idea here is that we put our device under test, the chip we're going to test right here. This is a crappy Chinese copy of a 3M Textool ZIF socket. So I have to keep the part pushed down and push the lever that way when closing it, so it'll make contact on all the pins. We've got the bench power supply on now, so you can probably hear the fan from that. So what I'll do is kick on the power. I've got the current limit set at 100 milliamp, but this little guy only draws about 10 milliamps. It draws about half of what the original 8701 does. So here is our scope screen. Now the top blue one that's dancing around, that is the main clock input, which for NTSC is about 14.31818 megahertz. Bottom trace, that is the divided clock output, which is about the dot clock, which is about 8.18 megahertz. And that is what the trigger is, set the trigger on, is channel 1 there, that yellow trace. So that's why it's stable and the top one is not. But notice how stable that lower trace is. And we'll pop a real 8701 in there for comparison. So here is the real 8701, and take a look at the dot clock. Again, that is the yellow trace, and that is what the scope is set the trigger to. But notice how much jitter there is on that. And, you know, that's fine for the Commodore 64 and Commodore 128. It's not going to bother them a bit. It's just interesting that the ICS chip is so much more accurate in that regard. One interesting thing is when I was building this jig, I happened to have a package of crystals that I got off eBay, and I grabbed a random one, which happened to be this blurry guy right here. And that's the first one I put in this jig. Now I took the crystal out that was in there. And here's this random crystal I grabbed out of a bag of tin. And notice it's not doing anything. Sometimes it'll just try to start, but most of the time it does this. So I was thinking, you know, my layout on this circuit board was wrong, etc. And it finally occurred to me that maybe the crystal I put in there was bad. And sure enough, the crystal was bad, but luckily I had socketed it, so I was able to use it as a crystal tester. And I tested all the other 9 crystals that were in that bag, and they were all just fine. One of the beta testers shared with me that some of the C64 Reloaded Mark I boards have an issue with 8701 replacements when you have a high current draw from the user port. So I tried to duplicate this using a real Commodore 64. So here we have the user port of this Commodore 64 connected to this little prototyping board here on the front left. There is a MOSFET on there that is controlled by CIA number 2, and that MOSFET is turned on from, you know, a few times a second to a few thousand times a second, and that puts about a 200 milliamp draw on the 5-volt line at the user port. I wasn't able to duplicate the problem, and I decided to try to simplify the test setup. And I reconfigured the little prototyping board so I could dynamically control the voltage going to the clock chip based on an input signal from my function generator. This let me dynamically vary the voltage between 4 volts and 5 volts from a few times a second to a few 100,000 times a second. And I was not able to get the ICS 525 based 8701 replacement, i.e. the little board I made. I was not able to get it to stumble, whereas it would run in all sorts of circumstances the original 8701 would not. I did a static voltage test and I found the original 8701 would run down to about 3 volts, whereas the ICS 525 based replacement would run down to about 2 volts. Well, this was very interesting, and it let me see that this little clock replacement that I had made worked rather well. The problem with the Mark I board is a problem with the Mark I board, and I don't have one, so I'm not going to be able to solve it. I suspect, though, that if you added a little extra bulk capacitance at the user port on the Mark I board, then everything would be fine no matter what you had plugged into that port. Just as I was getting ready to finish up this video, look what showed up at my door. This little blue box. And what was inside but a bunch of little blue boards. So you could make your very own MOS 8701 replacement. Let's build one up and we'll try it out in this Commodore 128. Wow, that was fast. Let's plug it in and we'll see if it works. Hey, it works. So I hooked up Sven Peterson's diagnostic test harness here to the Commodore 128. He also has the proper keyboard dongle for the 128, and it's been running fine. I did make one mistake though. In my excitement to get this set up, I plugged everything in and turned it on, and I thought, oh, I forgot the monitor cable. So I plugged the monitor cable right in, and then thought, oh no, I didn't turn the power down, and yeah, I blew up the SID chip. So don't be like me. Make sure your Commodore's powered down before you plug in your monitor cable, or anything else for that matter. Anyhow, the clock chip works great. It's been sailing along now close to 15 minutes with no problems. I realized it might be kind of hard for other folks to duplicate this just because of the Z-bent pins. So I found a good deal on some of these clock chips that I'm using, and I ordered some circuit boards and the other parts, and I put together a little kit, which I'll have on my website, and I'll put the link down below. The kit comes with the circuit board and all the parts, including the clock chip. The only thing you'll need to provide is some sort of soldering fixture. Now, you can make one, like I'm showing here, out of 3 layers of single-sided perf board material that has about 1 millimeter holes in it. Just line up the holes, glue it together, and you're set. The purpose of the soldering fixture is to keep the legs perpendicular and lined up while you're soldering them on. That's it. Now, I'll put a link to the kit in the description down below. And I'll also break out just the soldering section of this video into its own little video, so that'll be easier for reference purposes. And I'm also going to write up a little how-to manual with some photos in case that's easier for some folks to look at the photos instead of watching the video. All the files for this project are on my GitHub account, and I'll put the link to that down below. It includes the design files for the circuit board itself, for the testing fixture, and for the little fixtures to put the Z-bend in the legs. There's a few of you out there that would like a pre-assembled and tested board. Those will be available as well. Of course, those are a little more expensive because it takes time to build them and test them, but they're still pretty reasonable, I think. Again, the link to that is down below. If you have any questions or comments or ideas for future videos, just leave them in the comment section down below. I would love to hear from you. I'd also like to take a moment to say thank you to all the folks who help support the Hey Bert channel through Patreon and other means. It's greatly appreciated, and you help keep this channel going. If you'd like some more information about that, just look in the description down below. If you're a subscriber to the Hey Bert channel, I would like to say thank you. It's very encouraging to watch the number of subscribers go up, and it helps other people with similar interest find the channel as well. Now, if you're not a subscriber yet, what are you waiting for? If you look down below, you'll see a rectangular button that says subscribe, and if you click on that, you'll be subscribed to the channel. Then, if you click on that little bell-shaped icon, YouTube will let you know just as soon as I post a new video. Well, until next time, bye.